morning. These guys thought of some crazy stuff. Yeah, works. Thanks, Sanjay. Yesterday, some of my friends referred to me as Professor Sikka, and our geniuses thought of doing a 45-minute class by the CEO of a company to more than 1,000 people from diverse business backgrounds and diverse parts of the world. And if you just think about how exactly is this going to work, and now we are 15 minutes late. So that is the situation. Friends, fortunately, there is no AI who could solve this problem, so we will somehow make this work. I have 45 minutes to give you what is it called? Under the hood, Claire? Under the hood introduction to AI. So I'm going to try and do this in 3 parts. I'll give you a brief overview. Can you guys see the screen okay? Can we put the screen up? Ah, good. AI under the hood. I'll try and do a brief introduction, hey Rajesh, for 15 minutes, and then we'll show you a couple of examples under the hood for 10-15 minutes, and then I'll show you what I think you really care about, which is what kinds of problems can we solve for 10-15 minutes, and then hopefully we'll have a few minutes for Q&A. Does that sound about good? Right, all good in the hood, under the hood? Okay, so AI, of course, is something that is the pursuit of building something intelligent is something that is as old as humanity, going back to Greek times and even before. But really, the field of artificial intelligence started in 1956. There was a group of scientists that came together at Dartmouth in the summer of 1956, and there unfortunately they did not have detailed notes from that meeting. They were there for a few weeks, and they created what now we refer to as artificial intelligence. And 2 of the fathers of AI, Marvin Minsky and John McCarthy. John McCarthy came up with the name AI, and Minsky gave it the first definition, which was that AI is the science of making machines do things that we would consider intelligent if done by people. My own personal connection with them is they were both great teachers of my life. John was the head of my qualifying exam committee at Stanford during my doctoral studies, and Marvin wrote a brief letter of recommendation for me to Stanford, which changed my life. Marvin passed away last year, and John McCarthy passed away a couple of weeks after Steve Jobs did. And of course, Steve Jobs' passing was incredibly widely covered and celebrated and discussed and talked about, as deservedly so, obviously. But literally 15 days later, John passed away, and arguably the greatest computer scientist ever and the inventor of the field of artificial intelligence, and barely anyone knew who he was. Since their time, there has been a tremendous amount of work in AI. It went through many different phases. There was a tremendous amount of excitement in the 1960s and 70s. Lots of progress was made. Then in the early 90s, around the time when I was a student, that time was referred to as something called the AI winter, because progress had slowed. And already by this time, various different schools of thought had started to emerge in AI. And But progress had slowed, so people started to branch off things. Machine learning actually started off as a field around that time. Several other aspects of AI that started to get relevance, started to come up with different names and branch off from the broader field. And then, of course, more recently, some more breakthrough advances happened, which have reignited the interest in AI. And these are largely the result of 3 researchers, and then, of course, many others related to them in the field of deep learning, which is a particular type of AI. So let me, first of all, say that it is incredibly absurd to try and do a 15-minute overview of what is going on in this vast field. So I will point you to a few places where you can start if you are interested. There is a wonderful book, a very comprehensive book by Russell and Norvig called AI. It's called AI MA, Artificial Intelligence: A Modern Approach. This is a very comprehensive book. Stuart Russell is working on the next edition of this. It will come out later this year, but the current edition is the 3rd edition. It's a very comprehensive book, and you can refer to that, read that up. A wonderful introductory paper, still relevant to this day, was written by Marvin Minsky. That's called Steps Towards Artificial Intelligence. My own lecture that I did for our employees, an hour-long lecture, was actually based on this paper. This is from before I was born. This is from 1963, I think, or 1962. But it is still a very, very comprehensive and wonderful introduction to the field of AI. Anyway, there is also a very nice class on edX called CS 188, which is probably one of the best AI introduction classes. Udacity, Sebastian was here, and in the previous discussion, the panel discussion, and Sebastian and Peter Norvig, this co-author of the book, they have together done an introduction to AI on Udacity. That is a wonderful class. There is also an introductory class at Coursera on AI. So if you guys are interested, those are some good places to start, and then follow along from there. Intro to AI online class. Okay. Generally speaking, what has happened in the world of AI? Guys, can you turn the clock on at 35 minutes so I know how far along I am? Thank you. So, generally speaking, you can categorize the world of AI. Obviously, it is the science of making machines do things that we would consider intelligent. So there is a system, and then there is the world around that system, and there are inputs going into the system from the world, and then there are actions that the system is taking to affect the world. And so the system needs to develop the abilities to do perception of what is going on and then take actions based on that perception. So this is basically the idea. So what has happened is that, let me add a new one and hide that. The world of AI has sort of broken into these 2 big buckets. You can call it the neat AI and the scruffy AI. And this is not my terminology. This is actually terminology that is quite old. And the world of neat AI thinks that we can build intelligent systems very neatly by capturing the world, modeling the world, and so forth. And the scruffy world, where we have neural networks and new kinds of approaches which are scruffy, which are messy, but they work. And to more quickly describe this, let me go to a slide. So the world of neat AI characterizes AI where the intelligence of the system is based on a symbolic view of the world. So if you look at my picture here, this, what is going on inside here is a bunch of symbols that we can understand. And that is not always possible. But anyhow, so you are describing the world as a symbol system. Actually, two of the founders of AI from Carnegie Mellon University, Alan Newell and Herb Simon, they had a thing called a physical symbol system hypothesis, which was that actually intelligence is characterized by something that can be represented as a physical symbol system. So you represent the world as a symbol system and you model, perceive and reason about it. So in other words, you are observing some kind of a behavior and then you create a model of that. And then this branch of AI, which is decades of work by tens of thousands of researchers, has many approaches. We are all familiar with many of them. The very basic ones are, of course, the statistical models, where we represent some particular behavior as a statistical set of models and operations. Statistical models have their own limitations. They are quite dense mathematically and so forth. And they are also symbolically, from a symbol perspective, not very expressive. So many approaches showed up over the last many decades, which are more expressive than statistics, logic-oriented approaches where you represent the world using logic. We can broadly characterize those as knowledge representation and reasoning, which means that you are representing the knowledge that you have about a particular piece of the world, and you are using some kind of a logic to describe that, and then the logic gives you machinery to reason about the infrastructure. So for example, those of you who have studied logic in school, you know the whole idea of all volcanoes are mountains, Mount Fuji is a volcano, therefore Mount Fuji is a mountain. That kind of a reasoning about representing the world and so on. And then of course much more complex kinds of logics, more elaborate ways of representing knowledge, creating knowledge graphs and ontologies and so forth. And some of the more powerful approaches, which are less strict than strict logic-based representations, are things like probabilistic networks, where you describe connections between various kinds of things using probabilities. And probabilistic networks or Bayesian networks. So here is a small example of a Bayesian network. This is in the world of, can you guys see this okay? This is in the world of disease, where you describe symptoms and their manifestations and so forth. So cancer metastasis, there is a probability of 0.8. It relates to increase in the calcium content in the serum. It also relates to the observation of a brain tumor, deep coma behavior or a severe headache behavior, and then the links between these nodes are the probabilities of those kinds of things happening. So it's a very powerful, very expressive technique to represent some complex thing. The problem with this is, I'll get to the problem with that. And here, of course, is a much more complex probabilistic network. This is without the probabilities, but it tells you that modeling real behavior gets into much more, much richer descriptions of what is going on. So one of the breakthroughs in this approach happened about 20 years ago, when people figured out ways to take large amounts of data to automatically create the probability. So you create a model, an empty model, and then the relationships between things inside the model were done by observing real data from systems. So this is a very powerful approach. Obviously, this whole body of work is extremely powerful. It is appealing because it is explicit and articulate. What does that mean? It means we can open up the system and we can make sense of what is going on. Here is the cancer, what is the probability? If there is indeed cancer, what is the likelihood of this thing resulting in a brain tumor? If there is a brain tumor, what are the odds of people showing up in a coma and this kind of a thing? we can understand what is going on. The system can express itself, it is articulate. If you want to ask why did you conclude that my behavior manifests as a flu, it can say, well, you know, your face was turning red, you had this fever, you have a cough, so all these mean that there is a 93% likelihood that you have a flu. But they are imprecise and inaccurate. What that means is that is a very fundamental thing. In the 1980s, when the first AI research was starting and people were starting to build the first what were called expert systems to do disease diagnosis or understand where oil might be or different kinds of mining problems and so on, people found that experts cannot articulate their knowledge, their know-how very well. And this is a very interesting phenomenon about our own brains. We know how certain things work. All of you who are experts in whatever it is that you do will be able to perform your tasks, obviously. But if somebody asked you, why do you think so? How did you reach that conclusion? Even when you very earnestly and diligently try to explain how you did that, those explanations are usually wrong. And this the AI researchers found in the late 1980s and early 90s was when they talked to the doctors, and they would talk to dozens of doctors and cross-check the things that they were telling and so forth. But what they would find was that the observations based on real data did not correspond to their explanations of them. And of course, now we know Tim Galway, who is a great tennis teacher, says that the parts of your brain that are playing tennis are not the parts that speak English. And so this is what is going on when we build these kinds of complex models, that even when we earnestly build them based on our understanding of how certain things in the world are working, they are not particularly accurate. However, they are comforting in that when we open them up, in cases where we can get them right, when we open them up, we realize that we can actually make sense of what is going on and we can compose them and so forth. They are also cost prohibitive, and that is a more technical discussion, that the nature of computation on these kinds of structures can be very, very expensive. So this is the world of neat AI in a nutshell, in a very unfair nutshell, and I hope I haven't offended many of the neat AI people. Is that all you talked about, what we did for decades, you moron? So the world of scruffy AI, let us do equal time injustice to both. The world of scruffy AI is very different. This world is based on a very powerful technique which has actually been around for many decades. Rosenblatt worked on perceptrons in the 1950s. And their idea was that, is there a simple mathematical structure? And there's a wonderful 2-hour lecture by Patrick Winston on how neural networks work, if you are interested, which is very accessible and also goes into quite a bit of depth, but it is very accessible for a non-technical audience. So long history from perceptrons to what are called supervised and unsupervised neural networks. This approach is also called connectionist approach. This is a numerical and number-oriented approach. And you basically have networks that kind of look like that. You take some behaviors coming into some perceptions coming into the system, you create layers of nodes and then connect them up in a network. And then the output layers are usually the outcomes that you are interested in. Either there are two nodes, one says, yes, this thing is a fraud, the other one says, no, this is not a fraud, or yes, there is a cat, in fact, a cat that is dancing in this YouTube video, and the other one says, no, there is no cat in this video. And so the network learns, and the way it learns is basically by many different kinds of approaches. The supervised approaches are where you feed this actual samples and say, this is a picture of a cat, and then it creates certain numbers in these intermediate nodes, and then based on the feedback that it gets, it goes back and readjusts those numbers over and over and over again over large amounts of data until it settles down into a very accurate representation of saying, okay, here is a cat in this thing, and this one may look like a cat, but actually it is not. So what has happened in this world is that in this particular world of scruffy AI is that there have been waves. So there was original work by Rosenblatt in the 50s and early 60s, and then Marvin Minsky showed a very interesting proof that some simple symbolic problems could not be solved by the simple perceptrons. Then another wave of research came up in the 70s and 80s, which showed that complex neural networks could be built and they could do amazing things. And I had a chance to work on these techniques in the early 90s. And then it kind of died down. But then in the last 20 years, especially in the last 15 or so years, there have been some remarkable advances. And there is a particular branch of this area called deep learning. And it is called deep learning because, not because there is anything particularly deep going on in there, but because the networks are deep. So there are many layers in the networks. And one of the reasons that that becomes possible is that there is massive amounts of computing now, large amounts of memory and huge amounts of CPU capacity that we can throw at these. And so we can build very, very complex networks which can find amazingly effectively the patterns. And Sebastian talked about skin cancer detection that he and his team did by looking at a few 100,000 pictures of skin diseases and which ones were cancer. And it actually has better accuracy now than any skin cancer expert. And it's an astonishing example of how these neural networks can learn to do very effective things. So there is these deep neural networks, and we can have so many layers inside them. The convolutional neural networks are called convolutional because the first few layers of those networks have convolutions inside them that create the categories, and then the subsequent layers create the segmentation or the identification of the specific patterns. Some other approaches that have emerged in this world that combine a couple of approaches, there is DRL, is deep reinforcement learning. Reinforcement learning is a kind of learning which is similar to how people learn, how children learn, where you reinforce positive behaviors and discourage negative behaviors. So you combine the approach of neural networks with this reinforcement idea of learning, and that DRL ends up being very powerful in many cases. And many of the autonomous car technologies are based on deep reinforcement learning. So this world has created a lot of excitement. So many of the recent advances, what you hear about AlphaGo, once again it won the Go match that finished yesterday in China. And so these are all examples of various kinds of deep learning. This approach is extremely powerful. There is a lot of excitement in Silicon Valley these days, is awash in deep learning mythology. And of course, there are significant issues with this approach. You can think of these as instinctive approaches. These are approaches to develop instincts. But there are no inferential abilities. You cannot go to Google and say, how tall was the president when John F. Kennedy was born? Even though it knows the answers to each of the sub-questions, and if it was smart enough, it could combine those into a proper answer like any 6-year-old can. So the inferencing ability is missing. And most importantly, they are not articulate. So if you open up one of these trained neural networks, you cannot tell anything. You cannot ask the neural network, why do you think so? If you try asking Alexa or Cortana or Siri or one of these agents that why do you think this is the right answer? And obviously, there is no ability to express, to articulate. Even in us, like I said, that ability is generally a separate faculty in our brain than the one that is doing the intelligence work. And so we are not particularly good at that either. Actually, Daniel Kahneman wrote an amazing book called Fast Thinking and Slow Thinking, which addresses some of this work. So the scruffy AI world, neural networks, is incredibly powerful. It's getting more powerful by the day. There are breakthrough results in image detection, fraud detection, autonomous driving, all kinds of areas which are very, very powerful. But this is still, there is a long way to go to get into more complex intelligent behavior. And yet, with what it has been able to do, there are lots of interesting problems that we can solve. So let me close this introduction with a So I mentioned the AI winter in the early 90s, and people used to reflect a lot on why in the 1960s, when the interest in AI was extremely hot, people had made forecasts that in the next 25 years, we'll have all kinds of things, voice recognition, natural language recognition, intelligent behavior, and all of that. And none of that happened. And so around the late 80s, early 90s, when I was a student, people used to reflect back on why was this happening? Why did we fail? Why were we in the winter at that time? And some of the interesting observations were that the problems that we were applying to were actually extremely simple problems. The blocks world was one of the famous things where you had a table with blocks on it, and it was an extremely simplified and a pristine kind of an environment in which people would try AI techniques. And then when they would bring them out into the real world, they would fail. And so in this time, Marvin wrote this amazing paper on neat versus scruffy. And where he made this observation that, and surely soon we will discover how to make symbolic representations that are more adaptive and connectionist representations that are more expressive. And you can see the overall paper and this paragraph is quite thoughtful. And of course, this is 26 years ago, and we are still not close to this. This is a wonderful depiction that was made by his daughter of, this is sort of the neat approach fighting the scruffy approach, and his view was that, of course, ultimately we'll end up with something like that. Okay. With me so far? Yeah? All good in the hood? So what can we do with all this? So to talk about that, let me bring Navin up on stage here. Navin, come on over. To show you some examples. I want to show you under the hood one real but somewhat simplified example of both of these approaches. One approach on the neat side and one approach on the scruffy side, and see what it can do for the very mundane problem of customer churn in a telecommunication scenario. But we were thinking about what is one application that everyone can relate to, and I think our customers abandoning us is one that all of us can relate to, especially at a customer event. By the way, we are not close to building an AI that could understand that joke. So Navin, you want to show, so what we are going to show you is a simplified customer churn example. One's done using a neat approach, which is we will look at a bunch of customer data. This is Rajesh, this is from the telecom world. We look at a bunch of data of people's telecom usage, and then we build a decision tree. We learn a decision tree automatically. This is all these are Nia examples. We learn to forecast which customer is likely to leave us and which ones are likely to stay. And then we'll do the same thing using a neural network on exactly the same problem, exactly the same data. And there is an important reason why I want to do that, which I'll tell you after we have done the thing. Can we show this?
So while this is getting set up, just kind of a quick story, as if some of you have worked with Vishal in the past, you know you don't have a lot of time to do these things. So Vishal calls me up at 11 o'clock last night and says he has a great idea on how we can change the demo. So in case this doesn't go flawlessly, I hope he'll cut me some slack here. So. Right, Vishal? So,
the other way to look at it is that the example that you had up until then was not a very good one.
That was always the reason. I never said Vishal's idea was a bad idea. So. Okay, so as Vishal said, what I'm going to do first is show you kind of at the guts of how a product like Nia might work. So I have a green screen. The idea is to show you how some of these algorithms work. So Vishal talk about the neat AI, scruffy AI. So I'm going to start with one neat example.
So you want to show the data?
Yeah, let me show the data. If you guys can see this giant Excel, right? It has about a very small number. Sebastian doesn't have 120,000 something rows, only about 2,500. So if you can read that, it kind of shows how long the customer has been with the client, and it has about evening calls they make, amount of time they spent in the evening calls, about, I think, 18, 19 columns. And the one in the end is about, so I've highlighted the ones where some of the customers might have churned, right? So it might seem like that if somebody makes a lot of customer service calls, so this person makes 4, this person makes 4, this person makes 5, and all of them seem to churn. But look at this one here, made only 0 customer service calls, but somehow still churned. So point being, I think, yeah, it's fairly complicated. And the idea is, can you actually predict when a customer might churn?
Real customer churn data, where all the signals relevant to customer churn would probably have a much larger number of fields. Here there are 20 or so fields. You'd probably have more than 100 fields in a typical telco situation. In retail, it would be even more. And our ability to understand how many signals impact the ability to forecast what is going on, of course, is also. So we're going to run this thing. We're going to learn a decision tree. Oh, you already did?
So already ran it. So yeah, it runs actually pretty quickly. So yeah, I ran on all the 2,500 rows. So I'll show you what it created in the back. But I think one thing to see is that it has this accuracy about 85%, which means that it's correct about 85% of the time. So if I maybe open up.
If you had run it longer, would it get built deep, or do you need more data to get better accuracy?
Yeah, usually a little more data, Vishal. So this is kind of the set on which I actually try to do predictions. If I can zoom this for some reason. Can you guys see it? Where's the view? So it basically got the prediction right in many of the cases. If you just look at the last column, the predicted one, and this is the actual one it's trying to compare itself against, right? And I think it gets most of them right. It kind of gets this one right to.
Pick one that it did not get
There's
right.
one here which it gets wrong, right? So that's kind of what the accuracy is trying to indicate you. It gets some of them wrong, right? So maybe show you how so Vishal talked about a decision tree. So let me show you what this one looks like.
So this is the graph that it actually builds in the course of learning the system, that in different conditions. So you can see, this is what I meant by articulate. The system can explain how it categorizes or classifies something as yes, this customer is likely to leave, or no, it is not likely to leave, by building this 4-layer graph of various conditions relating to whether they have an international plan or not, the number of minutes. Well, what do all these things mean, Navin?
So like this is the number of minutes they spend in a day, number of customer service calls that I pointed out, whether they have a voicemail plan. So these were all the columns that you saw on the spreadsheet, some 19 odd columns. So it tries to kind of make a judgment, and that's part of the training, how it should actually build this tree. So the only thing primarily I told the algorithm in this case is how deep this tree should be, the so-called depth. And that is a parameter that a good data scientist has to somehow figure out by looking at the data. So this is one of the challenges of actually building a good algorithm. Even though it gave about 85, 86%, that may not be good enough, right? So that's, just remember that, I'll come back to that, but this is one of the parameters, quote unquote, that one might need to tune in something like this. So I'm going to now run one of these scruffy ones, actually a neural network. This is actually running TensorFlow. So this takes a little longer. Because it actually has a different way of training. It's using actually the exact same data set. And so it finished. The main thing that you see here, the accuracy, slightly lower than the previous one, but don't pay too much attention to that. Again, as I said, this has not been tuned. Typically, as I think Vishal said, Sebastian said earlier, usually these networks need a lot more data to get more accurate. So I, again, only had about 2,500 rows. If I show you how this network looks like, not as pretty a picture as Vishal's, because made last night.
So this is the actual network. This is the topology of the network.
Yeah, so it has, as I said, so it takes all the 19 input variables, and Vishal talked about these hidden layers. So it has 3 hidden layers. The first one actually has 19, is fully connected. It is called what is called a feed-forward network. It has 2 more layers, and then finally it outputs a 1 or a 2, depending on whether to churn or not to churn, right? So again, as Vishal said, again, we use the same data. We showed you 2 different ways of doing it. But the challenge here now is twofold. How do I actually tune this? And then there are actually a very large number of algorithms like this, be on the neat side and the scruffy side. So how does a data scientist, people that are highly skilled, hard to find, a lot of money, how do you actually
So that is a very important point. So we now have tools.
Can we switch to this?
Yeah, let's switch to the other computer. We now have tools that we can go into the depths and we can apply data sets to specific kinds of algorithms. We can compare them. We also have tools, and this is what Navin is going to show you, is something that we have built in Mana. So you don't really need to get down to that level of detail that Navin was at. And you could run on the same data set many different approaches and see what they tell you.
So as you see, this is no longer a green screen anymore. So this is the same data set. So I can go in there. I can look at this data set. I can browse through this. So it's telling me, has a nice way of representing the data. The same thing that you saw in Excel, right? It's kind of showing you how the data is distributed, what are the columns that are so-called categorical, meaning they have non-numerical values. These are the distribution of numerical columns and so on, right? And so what I'll do, I will try to create, so what I want to show you is that the same data, I don't do any programming as a data scientist. I don't tell it whether to use the neat side or the scruffy side, or how to tune the parameters, what the depth of the tree should be, and so on and so forth. I want Nia to do all that for me. So I'm going to take this same training set. So the only thing you have to do, you have to tell what variable to predict, right? What is the dependent variable? So I'm going to pick the churn one. And if you can read in the back, it has this option which is called auto model, right? You can actually make it do a particular thing if you want to, but I'll not do that. I'll actually cut down the number of iterations that it runs. So that's all I do. I don't have to change anything if I don't want to, and I'll ask it to learn, right?
So now it is running a whole bunch of different algorithms, different approaches on that data set, and creating models automatically.
Yeah, so this takes about a minute, so I'll come back to it, but in the meantime, show you what the output might look like. So this is a model that had run a little earlier, exact same data, right? If I go inside this, maybe bring this up as a report. So it has done all this for you. So one of the most important things that matters to you as what are the most so-called predictive features. If you remember, it had 19 columns. Many of them may actually may not be that important. And that's really where a data scientist spends a lot of their time, figuring out what is the right features so that they don't, quote unquote, create an overfitted model, right? So in this case, it's saying the day minutes, these are normalized values. So day minutes is the most expressive. Then the customer service calls, as we thought, reflects that, and so on. I'll come back to this cost thing in a minute. And then again, the same idea about what your data look like, right? And then maybe show you this part of what it really did actually while it was running, right? So maybe a little hard to read, but it has tried actually 3 algorithms here. This is actually a different form of decision tree called gradient boosted. It's actually using essentially a forest of trees. This is support vector machines, or SVM. And this is a generalized linear model, something like linear models, but it's a little more complicated. But the idea being is that while it's running, it's trying these things. So dots that are higher are better. So it's quickly figured out that this GBT method is actually running a lot faster. If I look in here, this has, if you can read, its accuracy of about 94%. So if you remember, my previous one was about in the 85 range. I wrote all that code, but I didn't do anything. It self-tuned itself and actually came back and showed this. So that's kind of the main thing that this is doing, kind of automating, quote unquote, the data scientist.
Wonderful.
Right?
So that's a...
And this one is finished. This is the one that I just ran. So while I was showing you all this, it actually finished. It has the same things, that thing. This one actually came back with the accuracy of, I have to shift to the accuracy one, and right here, about 94%.
It's wonderful. So you take the 2,500 record data set, and you can do these kinds of things. Of course, outside, if you're interested, you can play with all these examples and have a more detailed conversation with the team. But what I wanted to show you was that we now have the tools, both on the neat side and the scruffy side, to do these kinds of things and even do these automatically. But the important thing is that what can we do with all this? One of the reasons that I wanted to show you the same problem being applied, two different approaches being applied to the same problem, is that the problem is still in command. The problem is still in charge. You are still in charge. These are techniques, even though they are very sophisticated techniques now, that the techniques are in service of the problem. So our ability to find the important problems is still what is most important here. So what are the kinds of problems that people are applying to? This is a generic list that I have here of use cases of Nia in various different industries. This is actually not particularly helpful because it has very generic motherhood and apple pie things like trading and disease prevention. Why don't we just put world peace here and call it a day? So here are some examples that we have actually implemented over the course of the last year in various different industries. If you look at yesterday I mentioned that we have roughly 160, right Sandeep, 160 implementations of different kinds of use cases that we have done with Nia over the last 13 months. And on the IT side, some of you are taking pictures, so let me make it clearer. On the IT side, even though we have 40, 50 IT deployments, they are generally in these three areas. So here is one around the new hiring. Whenever a new employee joins the company, that whole process of creating access and user creation and giving them access to different tools and systems and all of that, we have automated that particular activity using Nia. Service desk component, so you're taking tickets. This is one of the particularly relevant ones because it impacts a lot of the work that our teams do, taking large amounts of ticket data and automating the task of identifying which service desk should that be routed to, and pre-calculating, pre-assessing the answers, coming up with predetermined recommendations on what to do with a particular ticket and this kind of a thing. So you dramatically simplify the work that is being done by the service agent. Or this is again and also a particular one. There are tons and tons of batch jobs. You know, in 2011 at the VLDB conference, when we had done HANA, I had proclaimed the end of batch jobs, and now 6 years later, we are still, the world is awash in batch jobs. The failure prediction, the prediction of the failure of batch jobs, the analysis of those failures, and then fixing of the failures is one of these applications that we have deployed a couple dozen times. On the business side, and as I mentioned yesterday, the business cases are actually very, very, the business cases are extremely interesting Here is a data lake that we built for Hershey's to forecast the shelf life and demand, and so that you can become much more precise about restocking particular products into stores. There are some amazing examples here, understanding the purchase behavior across different channels, forecasting design costs. This is something that we did recently for an apparel manufacturer, one of the biggest apparel manufacturers in the world, forecasting the design cost, because they make hundreds of products in the course of a year, and going from an idea to what will it cost to actually make this product come to life, the raw materials, the ingredients of that product, and if you were to make a 500,000 of those, or 100,000 of those, or 10 million of those, what is it going to cost? Being able to accurately forecast that. Predicting the risk of GL accounts. This is one that I talked about yesterday, the labor union and contract document, a chatbot to analyze complex array of documents, regulatory documents, and then assist people in understanding their content, so that you can be compliant and simplify the work of the people who do that. Let me pick another couple that are they're all interesting, and you can talk to the teams about some of these. Of course, we did this one here that applies to every industry. There are many examples of predictive maintenance. This is a particularly interesting one, fraud prediction. Fraud is, of course, applying AI for fraud is something that has been done for at least the last 25 years. But now, the nature of fraud has become much more sophisticated, much more dynamic. So we need, we don't need a particular approach, we need a dynamic approach, we need a meta approach that can launch lots of approaches at the same time. In November last year, when the demonetization happened in India, very quickly certain unique kinds of fraud showed up. And all fraud detection systems failed because this type of fraud had never been done before, and it had particularly unique characteristics. So to be able to build an AI system that combines unsupervised and supervised learning with some human intervention to dynamically launch new understanding and new policy, new approaches in response to particular kinds of fraud that is happening, and to do that dynamically very, very quickly is something that is extremely important and valuable, and we can do that now. What else? Optimizing working capital management in mining, of course, cross-sell, upsell assistance. So there are dozens of applications that we have already deployed, and there is no limit to these. And as you can see, the number of, as we went along this exercise, the number of use cases on the business side ended up far exceeding the ones on the IT side, even though the number of deployments are roughly the same. Are they roughly the same, Sandeep and Navin, do you know? Do we have more business deployments or IT deployments? More individual business cases. But overall, out of the 160, how many are IT and how many are business?
So about 60 will be business use cases.
So there are 100 IT deployments across these 3 or 4 categories, but 60 business deployments across a much larger number of categories. So this was the interesting finding that we had over the last 12 months. So I have run out of time. Maybe we can, if there are any questions, maybe we can take a couple of questions. So this is what I wanted to cover. We are still early in the AI journey, but even within this journey, there is a lot that we can already do. Our ability to find the right problems and deploy these techniques on these problems is where the rubber meets the road, where the AI meets our humanity. And ultimately, my purpose in this was to give you a little glimpse of this, but also to, more than anything else, reinforce that once we learn more about it, once we become more aware of what is this AI stuff all about, and what are these neural networks, what are these decision trees and all of that, we realize that these are yet another set of techniques that people have built in the long history of techniques that people have been building for centuries. And we can do something about these to make our lives better. And that is more than anything else the lesson from all of this. Thank you very much. Oh. They will take that stuff away.
Thank you, Vishal and Navin.